Now we are going to talk how the data is written and then how the data is read, right? The first one is the write part. In Cassandra, we don't actually go and find, like in a table, what we do is we go and find a particular location to actually write data. In Cassandra, we don't do those things. What we do, it's a log structured storage engine, which means it's just a flat file, and then it blindly appends data, right? So when it blindly appends data, it just continuously appends it to the commit log. And that's the file that you see over there. But in a traditional RDBMS, it has to go to the right location and write data. So this seek time, for this operation, seek time's higher, and for that, there is no seek time. You just start appending data to the commit log. So there's no preset location for it. So here are some key components, like the first one is memtables. Memtable is the in-memory representation of your table in Cassandra with indexes. For every table in Cassandra, there is an in-memory representation in memtable. And then there's commit log. Commit log is just a file. It's append-only file, which means once written, it's written. You cannot go back and change data, which is where you get the speed, immutability, right? And commit log also serves another purpose. Because memtables are in memory, so if the memtables go down, you obviously have to restore the state of memtables from somewhere, which is where commit log comes into play. The node goes down, it comes back up, it takes the data which are there in the commit log and restores the state. And then comes the SS tables. SS tables stand for sorted string table. That's where SS comes in. And they are actually snapshots of memtables flushed to disk over time, because memtables are in memory, and memory is limited in terms of capacity. You have to write to disk at some point, and that's where SS tables come into play. And then comes the compaction. The first three are artifacts, so they're actually things, and the last one is a process. Compaction is a process where you have SS tables which are flushed to disk after time to time, and then you're going to merge all these SS tables, just like a Windows compaction if you want to think about it. But it's a bit more than that. One quick note, in the slides, if you go through the slides, well, the slides don't contain a lot of information, but then you see the presenter's notes over there, which has a lot of more detailed information. So I would really suggest you to go and go through the slides. They're quite self-explanatory. So now we have some pictures over here, nice animation. We can see how it is actually written. Coordinator is the node that a client picks in random. So it doesn't matter, Ring has, let's say, 20 nodes, right? The client picks some node in random, maybe the one that is nearest or with the lowest latency, whatever. So maybe in round robin fashion, there are various ways to pick a coordinator. That's more advanced topic, but let's say that's the node that is responsible for handling data write. So the client has contacted the coordinator, and the coordinator says, hey, I want to write. Partition key is a concept which is like primary key. Think of it as primary key right now, but we're going to get more into that soon. So the coordinator writes data into a node saying, hey, I want to write a record with partition key 3, first name Bruce, last name Wayne, of age 30, because I'm a Batman fan. That's why you have Bruce Wayne.
He's 30 years old?
Yeah, for me he is. He's a hero who never gets old. Huh? So then what happens is that this particular node, because why is it that the first question that comes to my mind is, why is it the coordinator not writing itself to the memtable and commit log? Well, the answer is that maybe the coordinator is not the owner of that hashed partition key. So you take the partition key, you send it to the murmur3 hash function, you get a value, some number between 2 to the power minus 64 to 2 to the power 64, and the ownership is the data has to go to this particular node. So this node is the one that has to write. So the coordinator says, hey, it's not my data, you handle it, and then it goes in there. And what happens is that that particular node first writes it to the memtable. That's the in-memory representation. Obviously, as you can see, everything above this line is in memory. Below this line is in the file system. And So the first operation is to append into the mem table, and simultaneously it's a parallel operation. It writes it into the commit log, and then what happens is that, well, if it writes into these two, then you get an acknowledgement from the node saying, hey, the write is successful. If the node goes down and the mem table gets destroyed, it can restore the state from the commit log. And then the client gets an acknowledgement, and that's it. The client doesn't worry about anything anymore. Or you can get a timeout exception, obviously. And then what happens is that after some time, the content in the mem table gets flushed to SS table on disk. And when that happens, well, you don't need that stuff in the memory, do you? So you clear it off, and then you draw a marker in the commit log saying that, hey, until this part, we've already flushed it. It's an SS table. We don't need you anymore. Why is it that this space is not reclaimed right away? Because it's time consuming. We will write over it. So that's why it's not emptied or reclaimed or whatever. And after some time, there is a periodic process called compaction that takes several SS tables and makes it into one SS table. Okay. Now there's one bit of information about commit log. Well, all these things are usually configurable in this file called cassandra.yaml, which is in the conf directory of Cassandra installation. We will get to that in a bit, but here's something that you have to know. Commit log also has in-memory writes. So everything that you think is written to commit log doesn't actually go to commit log right away. Commit log either writes in a batch fashion or periodically to the false. So it will wait until the batch value is 10, or well, you have the default value of 50 milliseconds. So then there's then the batch has completed and it syncs to disk. Or periodic commit means every 10 seconds it will write to the disk. So you think your data goes into the disk, well, you have a 10-second window, the data can be lost. Please bear that in mind. These things are obviously configurable in cassandra.yaml. Well, if you lower the value, then every time you write something, it goes into disk, and then you have higher latency, just to keep into account. And the reason why I'm actually going through these things are because these concepts are quite useful to actually understand the things that are there in the configuration file. If you don't know the internals, you will never make sense of what is there in the configuration file. It's just, Greek and Latin. Okay, the compaction process. The compaction process is quite simple. Why? Because you have writes over a time period, right? And let's take this particular case. There is Betty. What is the timestamp? The timestamp is 319, and then she has the name Betty as first name, and then at time 619 she said, well, that's a very funny nickname, I'm going to write my actual name. And then she says, my name is Elizabeth. So you have writes, these are happening over time, and then in SS table during compaction, what it does is it takes all these values and then merges it into one, and that's the compaction process. This happens during write so that the read becomes easier. Okay, well, it also does it for what is it called, deletion and expiration of expired entries. We're going to go through expired records because each record in Cassandra can potentially have something called time to live. Sometimes you want to have some data in your database that is only going to be valid for a certain time period. After that, you don't really need that data. So at the time, what we do is we can attach something called time to live, and when that TTL value exceeds that, then during compaction it's just thrown away. We don't need that. Well, one last thing, why is it necessary? Because if you don't do that, then your data is fragmented over several SS tables. When you read, you want to go and hit one SS table and fetch your data, right? Now you saw the easy bit. We're going to go to a more complicated bit, right? In Cassandra, the reads are blazing fast because you do one operation, right? You talk to the coordinator, and the coordinator in the end just talks to a node. It could be the same node or a different node, and it simultaneously writes to the mem table as well as commit log, and then it gets a response. So you have one operation. Let's look at read and see how many operations are in there. That's why read's about 10 times slower than write, up to 10 times, not exactly 10. So when you do perform a read, a client normally has a client driver. It could be for any language, like it can be .NET, Java, Node.js, PHP, whatever. It is talking to this particular node, which is acting as a coordinator because this is the nearest node for whatever reason. And this says, oh, well, I don't have the data. All the other 3 nodes have that particular replicated data, get the data value, and then this one has one with timestamp 523, 511, and 542. 542 is the greatest timestamp, it wins. Yeah? And if the other 2